I'm going to go through a quick agenda of what I'm going to talk about and how it fits into the overall agenda. So first, I'm going to situate myself within the discourse, as academics used to say. I'm going to use some motivating examples to try to explain why this topic is interesting to me. I'm going to talk about some inspirations from the world of learning art. And then I want to go briefly into ideas of software visualization and talk a little bit about architecture diagrams at the end. And so that whole thing I was saying earlier about situating myself within the discourse, what that really is just fancy academic language, meaning I'm going to introduce myself, but I normally hate introductions in presentations because they always seem so self-serving, but I just had some things I wanted to say this particular time. So as Ivana mentioned, I've worked at Intelliware for 20 years. Prior to working for Intelliware, I also worked for Manulife and IBM. I do a lot of solution architecture stuff, and Intelliware likes Agile. And when I joined Intelliware at 20 years ago, it was a much smaller company, and we actually used to get like this reading list. The founder of the company, Greg Betty, walked up to me one day with this big stack of books and said, "Hey, here is your reading list. Welcome to Intelliware." One of the books of which I fell in love with was The Visual Display of Quantitative Information by Edward Tufte. It's a fairly famous book in which he talks about, you know, how you can interestingly visually display information. And it's interesting that we're at a position now where all of a sudden people are starting to really care about the visualization of all kinds of data. This book has been around for quite some time, and the industry is in some ways only really catching up to some of his stuff. I graduated from University of Waterloo in 1990. I was part of the math faculty. And I always tell people that I have joint honors in pure math and theater arts. And every time I say that to people, people say, "Well, that's a weird combination. Why did you choose that?" And I always say, "Well, I kind of liked it because it exercised both halves of my brain." But it's interesting, once I've gotten out into the professional world, when people ask me for official bios for things, I always say, "B.C. Holmes graduated from University of Waterloo in 1990 with the joint honors in pure math and theater arts." And the editors who review such bios like immediately cross off that theater arts part because that's not important. We're a professional industry and nobody cares about the fact that I did some acting back when I was in university. So I always thought that was an interesting demonstration or an interesting statement about the value of different types of arts in the professional world. In the 2000s, I took night classes at George Brown College and did a wide variety of art classes there and got myself a cartooning certificate. I'm a certified cartoonist, which I think is really kind of cool. And it's in those classes that I actually ran across this fairly famous book called Drawing on the Right Side of the Brain, which is where I've lifted the essence of my title from. And it's basically a book about using the parts of the right side of the brain, which are very creative, very, you know, imaginative, etc., to make good art. A lot of art is actually trained in a very technical way. So you learn things like proportions of the human body and stuff like that. But this particular book was really trying to eschew all of that and just say, hey, you got to get into your feelings. You got to get into some, you know, really artistic side of your brain in order to do some really interesting art. And as a result, you know, this book has been continuously in print, probably for something like 40 years. In my spare time, I take that sort of cartooning expertise and I make comics, which is really kind of fun and exciting. Why, yes, some of these have been nominated for some really interesting awards. Thank you for asking. So why do I make that? Why do I go that introduction? So my point here is 3 points. So A, I really like art and visual stuff. It's just in my DNA. It seems like I'm just constantly drawn to it, etc. I really like visualizing stuff, and I think that the process of visualizing stuff makes it easier for me to understand it. Maybe that's just the way my brain is wired. But I actually think I'm not alone in that. I think a lot of people are able to understand stuff better when they can actually visualize it and see it in their heads. And then lastly, I think that, you know, pictures help me explain technical stuff to non-technical people. So, you know, like a lot of people who do architecture-related stuff, I sometimes find myself thinking a lot of really complex stuff and a lot of really strange technology and trying to explain often to business people or people who are not technical why this is important and why they should care about it. And pictures just help me bridge that gap because people can relate to a picture in a way that they can't relate to a whole bunch of technical jargon. But maybe I'm biased. Like, you know, it could be that this is just really idiosyncratic and I'm the only one who thinks that way. I don't think that's true, but these sorts of points have been rolling around in my brain for a while, and that sort of is what motivated me to actually try to write this presentation and put it together. I will say that I'm putting this presentation together with a bunch of caveats or a bunch of things that I think make this whole topic complex. So one point is, like, our industry is painfully aware that STEM skills are in huge demand, and there are nowhere near enough people who pursue STEM skills. And this is doubly important when we're talking about women in STEM professions. I think we have a long history of knowing that there's something about the STEM world that seems to push women out of it and try to encourage them to think, oh, that's not for you. Why don't you go take English classes or something like that? So it seems a little weird to sit here and say, hey, no, visual arts are great, when I know that there's all this social pressure to say, hey, women, get out of STEM fields, and we need to push back against that social pressure that does that. I think it's also true that we live in a society that doesn't value most forms of art and doesn't want to pay artists well. So it's a little weird to say, hey, art makes me a better programmer. Knowing that we live in a society that says, no, if you call yourself an artist, then you're basically, saying that we can pay you a small amount of money. Whereas you call yourself an engineer, then we should have to pay you lots of money. And it's even true in the technical industry that the closer you are into something that seems like it's art related, the worse you're treated and the worse you're paid, et cetera. So, if the thing that you produce is something that creates spreadsheets, like, that's worth a lot of money because you're helping the banking industry. But if you're a video game programmer, and doing stuff with 3D, et cetera, you get paid really badly, et cetera. These things are just true of our industry. And so it's a little weird and sad to have to talk about, the role of art in technology when art is not valued in the technology world and art is not valued in our society in general, in my opinion. So I want to talk about a handful of motivating examples. You may have heard of some of these examples before, or you might not have. So my first example is one that I think a lot of people have probably encountered before, and that has to do with the Columbia shuttle disaster. And so Columbia was the second shuttle that blew up. As a lot of people know, that the fundamental problem is when it took off, a piece of foam fell off of it and damaged one of the wings, and when it came back to Earth, that hole in the wing caused gases to come in, and the whole shuttle blew up. And the part that's really interesting about this whole story is that after the takeoff, people at NASA saw the fact that they took some damage during the takeoff, and a bunch of engineers at NASA were scratching their head saying, I don't know that this is necessarily safe anymore. And I think that we should, take a double look at that shuttle just to make sure it's safe to come in. And they were largely ignored. And part of the reason they were largely ignored is because they sort of sent this slide off to the head bigwigs at NASA to explain why it was that they wanted to actually investigate it further. And I'm not going to go through this point by point, but this slide is impenetrable. Like, this slide is terrible. There's nowhere in this slide that it says, hey, shuttle could blow up on re-entry. We need to take this seriously. It's an awful slide. And there's a really interesting blog entry that kind of like looks at the various points that are wrong with it and makes these 4 summary conclusions about what's so bad about this particular slide. I think Tufte even wrote a whole booklet about the horrors of PowerPoint, motivated by this particular slide. So the person who made the blog entry says, A, you need to summarize your key points of the title. B, you need to minimize the number of bullet points that you're throwing out there, because the brain can only really hold a certain amount of information at any one time. C, like, this whole bit about sub-bullets is just asking for danger, because you're just increasing the amount of cognitive load on people. And I'd really like this 4th point, which is that, hey, pictures are better. And so the blog post I'm talking about propose these alternative slides, like, hey, this would be a great picture to give to the NASA higher ups and say, something's bad. We need additional in-orbit photos of the wing. And, at the best case, they've hit the side of the wing, and that's kind of cool. But in the worst case, they've hit the edge of the wing, and that's really, really bad. And you could go through with some of these other points as well. So my point about that example is the way that we present information matters. And we can present information better, knowing some ideas about visual rules. The second example I want to do is a silly magic trick. I remember learning this trick back when I was in math in the University of Waterloo, and talking to my topology professor one day. And so the whole point about this has to do with, that stupid magic trick where you have these 2 rings, and, magicians have some trick where they can actually separate part of the rings. But in the real world, if you have 2 rings and they're caught together, we kind of know fundamentally that you can't actually, pull them apart. And so if you think about this in 2 dimensions, those rings are actually always touching each other. So you can never really pull them apart because, they're stuck to each other. But if you think about it in 3 dimensions, you can recognize that it's really hard to pull those things apart, because you just hit this point where they connect with each other and you can actually like pull them through each other without causing damage to one or the other. So now here's the interesting question. Can we separate these two connected rings in 4 dimensions? And I'm going to say, yes, we can. And all you have to do is like visualize this in 4 dimensions. And if we were in a room full of people, I could look out into the crowd and see who looks really confused at this point when I'm talking about visualizing things in 4 dimensions. But visualization is a cool thing. Like all you have to do is imagine somehow, how do we see the 4th dimension on a particular image? So if you look at that particular 3-dimensional image on the right of my slide here, you recognize that this is a 2-dimensional image that is representing 3-dimensional images. My slide is 2 dimensions, but you know, I've done shading and I've got, you know, shadows, and you can kind of understand that it's projected onto, it's a 3-dimensional image projected onto 2 dimensions. So how do we project a 4-dimensional image onto 2 dimensions? Well, all we need to do is have some way of representing the 4th dimension. And so we just need some sort of convention to say, what does the 4th dimension look like? What if we use color? Color is a cool thing. So at one end of the color axis, you imagine it's like dark, dark purple, and the way other end of the color axis, we imagine that's, you know, bright red. And so moving this in the 4th dimension is just a matter of moving it through color. So if I take one of those 2 rings and just start shifting its color down from blue to green to yellow to orange to red, now it is moved in the 4th dimension. Now I start moving it, you know, in one of the normal dimensions, and I'm going to hit that point where I think that they're going to connect, except that I know they don't connect because one of them is orange and the other one is blue. And so the one coordinate of those 2 rings doesn't match, and therefore they're not really connecting in 4 dimensions. So now I can just pull the 2 rings apart. Cool. Visualize the problem in 4 dimensions. So what's my point there? The right visualization can aid us in understanding a solution, even a really kind of weird solution like that. How do you visualize rings in 4 dimensions? All you just need is a visualization trick there, and that can get you over a lot. I have another example here that I want to use because I always find it really interesting, and it speaks to me in terms of visualization. Several years ago, we built this pharmacy system. Some of my colleagues at Intelliware, you know, probably get tired of me referring to the system, but I think it's so interesting because it trips on what I think is a number of interesting failures of visualization. And so the point here is that we built this pharmacy system. You know, if you go back to the back of any old pharmacy, you'll see the pharmacy area. You know, there's usually a spot where you take your prescription up, you drop it off there, and then they send it to somebody who works back behind another desk and they fulfill it. And sometimes they may use, you know, some automated filling machines, or maybe they just do it manually and they count out the number of pills and dump it into the pill bottle. And ultimately you end up going to this other station where you pick up the prescriptions and can probably pay for it there at the same time. And that's all really cool. And so we built that system. And in the absence of anything better to think about, we started thinking about what are the things that exist inside of a pharmacy system. So we imagined, you know, the prescription, we imagined, you know, the fills, the pill bottles, et cetera. We imagined the pharmacists and doctors, and those were the fundamental things that we represented in the actual code. So we had to sit down and we had to say, hey, what's our code going to look like? And so we had a prescription table, and we had a, you know, refill table, and we had a doctor's table, et cetera. And we built all those things into the system. And it wasn't until fairly late that we realized, actually, we were thinking about the wrong things, because the most important part of that whole process was not to be able to represent prescriptions and not to be able to represent the doctors, but the most important part of that system is that we need to be able to represent the flow of the fill of a prescription from beginning to end. And in essence, what it really should have been like was more like a conveyor belt. Like that was pretty much the better representation of trying to figure out how the system should have been built. And if we had imagined it like a conveyor belt, then we would have thought about it differently, and we would have implemented it differently. And we would have said, really what was happening is we were having work that was moving through the system from station to station. And it was while it was going from station to station that most of the interesting business logic actually needed to be applied. But because we didn't think about that, when we never visualized the conveyor belt, we kind of got that wrong, and we built the system wrong for a good long time. And finally we had a correction to that and said, okay, I think we built the wrong thing here. We need to shift gears on this. And that example, the point of that example is, I think people will fill in a visualization in the absence of one that's being presented to them, and it might be the wrong visualization. So that's another example. And I think that ties into another point that I'm interested in making, which is that we're Intelliware, we're an agile company. 20 years ago, you know, we tried to codify our own internal agile practice that we call iProving. And it's evolved a lot over the last 20 years. But 20 years ago, it looked and smelled a whole lot like Kent Beck's extreme programming concept. And so our practices, shared a lot in common with the extreme programming agile practices. We had user stories, we had pair programming, et cetera. But there is one practice that we didn't include, and we replaced it with our own practice. And the one that we inserted there was called architecture seed. But the one that we replaced it with was actually a thing called metaphor. And I'm telling a trade secret here about why it is that we didn't use metaphor. And just to remind people about what extreme programming says about this, this is a practice to guide all the development with a simple shared story about the whole system works. And so why did we not use the metaphor practice? The truth is we never fully understood it. We didn't really have a whole lot of good examples to go on. We had good examples of what user stories look like. We had good examples of what test cases look like. We had good examples of what pair programming looked like. We never really had a number of good examples about what a metaphor looked like. But I think metaphor as an agile practice was trying to put some languages and some words around this idea of you need to have a shared vision or a shared visualization among your programmers in order to make sure that everyone was sort of on the same page in building stuff. And I think that, that idea about the conveyor belt visualization for the pharmacy system was an appropriate metaphor that we probably should have gone through. I'm just checking on the time here and realizing I'm gonna have to speed up a little bit because I've got way too much information. I'm constantly over preparing for things and having too many slides, so forgive me if I start racing through some stuff in a little bit. So I want to talk a little bit about learning art because I think that learning art is a really interesting thing. I first encountered some disconnect, I guess, between the way I thought about things and the way that a lot of my colleagues thought about things several years ago during a presentation about creativity. So we had somebody internally who was talking about the role of creativity and how to be more creative in the way that we actually implement stuff. And the thing I kept tripping on is that they had some ideas and practices about how to increase your creativity. But one of the things that struck me as really absent, and which would have been obvious to anyone who comes from a theater background, is that in theater, creativity is generally thought of like a muscle, and you can warm it up and you can practice it. And there you can do exercises to, get your creativity hopping, etc. And nobody in the IT world talks in this language, and I think that's really interesting. In tech worlds, whenever you have to go into a session where you're brainstorming or something like that, it usually starts with, hey, we have sticky notes, and obviously now it's the time to be creative, go at it, etc. And so this idea that, sometimes you learn art in a particular way and it teaches you certain things and certain ways of looking at certain things, and those aren't necessarily shared in the way that we learn tech stuff. But I think there's value in learning some of the stuff that about how we teach and learn art. In particular, my keyboard is giving me problems. In particular, I think one of the reasons we don't tend to want to see value in the way we learn art has to do with this narrative or this myth that exists about artistic talent, and that people go into the arts and the visual arts because they have talent, and every teacher that I've ever had basically rejects the idea that talent is a meaningful concept that's worth talking about in art, which surprises a lot of people. Every single art teacher that I've had has always said that basically art is a learned skill, and you practice it and you practice it and you practice it and you get better, etc. And talent is just a ridiculous concept, and in fact it's also a very recent concept that for most of the history of art, people have not talked about learning art. They talk about apprenticing, and they have not talked about talent in terms of art. They talk about apprenticing, they talk about practice, they talk about spending time learning the craft, but this idea about talent is a very recent concept and not a very healthy one. And so, I'm going the wrong direction. So a good way of talking about some of the practices of learning art is to look at a particular set of videos done by this guy named Andrew Price. I happen to be familiar with Andrew Price because he does a lot of work in a 3D modeling tool called Blender. And a few years ago, he did this presentation at a Blender conference in Amsterdam that was called The Habits of Effective Artists. I think he originally wanted to call it like 7 Habits of Effective Artists, but the 7 Habits of Highly Effective People guy claimed that was copyrighted, etc. And so he couldn't do that. but he recently updated that video and revisited this whole idea of the habits of effective artists. And basically, he encapsulates some of his ideas about, how you actually grow and improve as an artist. And I think that a lot of those ideas that he's talking about actually can be applied to the way that we grow as programmers and become better as programmers. He actually talks about 10 different practices that are worth talking about. I just don't have time to go through all of this, unfortunately. So I'm just going to talk about a couple of those, which I think are really interesting. Because I think that there's something to be learned from looking at some of these practices. One of the practices that I think is immediately applicable to people who are trying to grow their technical skills is the whole idea that if you want to improve your drawing ability, you should draw every day. Like, that's the #1 suggestion that comes from every art teacher I've ever encountered. And I think that, if you want to improve your coding ability, you should code every day. And I don't necessarily mean code every business day. I mean, like, code every day. And a lot of people, will think, I can't code every day. It's like, there's often stuff that's impeding me from coding every day. And there's actually a fairly straightforward response to that, which is like, if nothing else, you should do the bare minimum. Like, if you can write 1 line of code, or you can, start 1 class, or, start the very beginnings of 1 thing every day, like that practice in and of itself helps you to improve. Andrew Price talks about the example of rap musicians, and he says, like, rap musicians, like so many other artists, go through periods of artistic block where they just kind of feel like they can't get anything accomplished. And when they get into that particular position, often producers will say, okay, well, can you just go home and just write 1 word of your next song? Like, that's it, just 1 word. And that's an amazing way of, like, just popping that artistic block that they're encountering. They go home, they write 1 word, and sometimes that's all they accomplish. They just manage to get 1 word. But just the very act of being committed to going home and writing 1 word just sometimes opens up the floodgates and allows them to proceed forward, etc. Another example that I think is really interesting is the practice of stealing. And stealing is an interesting term in the whole art world. Because, outright plagiarism is generally considered to be a bad thing. But, taking inspiration from, and sometimes, more, is actually a pretty fairly common practice. One of the things that stealing is really useful for, when I was learning a lot of art classes, is one of the exercises that we'd often do was reproduction. So we would find, a piece of art that we were particularly interested in, and we would have to reproduce that using our own tools, etc. And that whole exercise of reproduction of existing art was a thing that helped us to learn techniques of other people. And I think that that's a technique that a lot of people can benefit from in the coding world. So I think that if you are interested in coding, and if you are interested in improving your coding, in particular improving, good new heuristics and trying to be faster, etc., I think you need to dig into a whole bunch of other people's stuff. If you're on a project with a team and you're sharing code on that project with other people in that team, chances are you're seeing other people's code, but they're other people who are often very similar, who code in a very similar style to you. I think there's a lot of value in going out and looking at and fiddling with code that isn't yours and learning to understand it. I also think that there's a whole lot of value in growing the skill of reading strange code that you're not familiar with, basically. I think that the ability to read and discern the overall impact of that particular code is an important skill. I had an experience once where I was at a museum in New York with a friend of mine, and there was a performance of drummers there, and my friend was a professional musician, and she enjoyed the drumming and pulled out a piece of paper and wrote down the tune. And I looked at her and said, "What did you just do?" And she's like, "I wrote down the tune. I thought it was an interesting tune, so I wrote down the tune." I mean, what do you mean you wrote down the tune? How do you write down the tune? What notation to use? And so she showed me the piece of paper, and she'd written the music on the piece of paper. And I was just perplexed by that, because I have never known musical notation well enough to be able to just hear music and write it down as music. But, that was something that was necessary for her profession, because she was a professional musician. She needs to be able to translate from the notation to the music and from the music to the notation in order to be good at her job. And I think that that is a skill that is necessary of coders as well. I think you need to be able to discern the meaning from the code, and you need to be able to take the meaning and then create the code that actually does it. And I think that people are better at the latter than they are at the former. And I think that that's something that holds a lot of people back. I'm going to go back to this idea of stealing code. There's a quotation that I actually think is really interesting from somebody I think is one of the greatest comic book creators of all time, which is a guy named Wally Wood. He says, never draw what you can swipe, never swipe what you can trace, never trace what you can photocopy, and never photocopy what you can clip out and paste out. And I mean, that's a pretty extreme point of view, but you know, he legitimately says, like, this is the way, you know, an artist should go about things. And I think that that's, I think you could be too literal about that, but you know, this is a piece of guidance that's been repeated by countless comic artists over time. Another really interesting piece of guidance is this guidance from Gary Panter, who's also a cartoonist. He says, you know, basically talking about inspiration and drawing and models, who are your models for the work that you do. And he says, if you have one person you're influenced by, everyone will say you're the next whoever, you know, but if you rip off 100 people, everyone will say you're so original, which I think is a really interesting idea about how the art world is viewing the sort of idea about developing, but learning from all of the other people who have been artists as well. So because of my interest in the visual arts, I spent a lot of time really interested in software visualization. And so just to remind people what software visualization is, the software visualization is the process of understanding software systems by, you know, figuring out a way to turn that into something visual and then analyzing the visual thing to understand what's happened. I'm not gonna lie, software visualization has never really been mainstream. So it's hard to claim that there's great successes here. And the reason that it isn't mainstream is that it's either that the tools are bad or they're very expensive. You know, there's a tool out there called SonarQube, which is pretty commonly used in Java projects, maybe some other projects, but it has some scope limits. So why do I think software visualization is interesting? Why do I keep returning to it? And I think this quotation is a really interesting one, which is that the idea that programmers tend to adapt to the level of representation provided by the computer instead of adapting the computer's representations to their perceptive abilities. So we all interact with, you know, code because that's what the computer easily offers us up. It offers us up text. And we as people are actually able to perceive things in a lot of additional ways. But at the moment, it's hard to get the computer to show us those things in other ways. And so we just like accept that this is the way the computer is giving us the information. So that's the way that that's the level that we stick to, and often don't demand more out of the way that our computers show us software. So software visualization, I think, is a thing that can help us with some legit problems. In particular, it can help us with understanding systems that we ourselves did not start and did not write. So I've been on a project for a little while where people have handed us some code that has been created, you know, by a completely different company, by people I don't know, in languages that, you know, are not my preferred languages, and that, you know, have been around for so long that nobody has documentation about just about anything. And wouldn't it be great if I could just like run some analysis on that particular code base and say, okay, this is now showing me a visualization of the actual code here, so I can help understand that. Robert Martin, Uncle Bob, as they call him, once said that the ratio of time spent reading code to writing code is well over 10 to 1. So we are more often in the position where we have to read code than we are in the position of having to write the code. So wouldn't it be great if code that exists was easy to read and easy to process and easy to conceptualize, because it was in some way, you know, easy to turn into some sort of visualization. There's a blog post as well that, you know, by this guy named Peter Hallam, who argues that, you know, we spend something like 78% of our time reading the code, 20% modifying, and only 2% writing the code. So writing code is an interesting thing. We spend a lot of our time thinking about how we write code and how we write code better. But really, if we are good professionals, what we should be caring about a great deal is the fact that we have to read that code, and even worse, that some people who are nothing like us and who we don't necessarily know about in advance might have to read this code in advance. And part of the reason why visualization is so interesting is that there's a whole lot more stuff that you can get out of visualization and graphics than we can get out of text. So we can understand stuff positionally if it's visual. We can understand meaning of size fairly easily if it's visual. You know, we can distinguish between shapes of visual things. We can understand the distinctions between the orientation, the hue, the color, the texture, etc. And, you know, there are some very simple ways in which we sometimes see this stuff in our IDEs of choice. You know, it's fairly common these days for IDEs to color code keywords and stuff like that. But we're really in the very basic earliest elements of trying to represent code visually when we're dealing with IDEs. You know, it's at level 1, and we need to, I think we need to go to something like level 10. It's also true that, you know, good visualizations are things that help our brain really understand things quickly. There's a lot of research that says that, you know, the outliers in these 3 sort of blocks of circles that I've got here, our brain sees them in something like 200 milliseconds. You know, that's far faster. I can see that far faster than I could read through a wall of text and try to find the one outlier, etc. I think that we understand that conceptually because now we're in a place where we're increasingly looking at logs in visual ways in order to understand activity that's happening in systems. So, you know, if for whatever reason, you know, on Thursday night, we had 10 times the amount of traffic to our application, we're not going to see that by looking at the text of logs going through, but we will see that if we pump that log into some ELK system and we visualize the log volume and we suddenly see the spike going up on one evening and it's much higher than all the other evenings. And so visualization is clearly understood in several areas to be a better way of taking in information, but we haven't used that a whole lot to help us deal with the way that we program things. And there's also a whole bunch of other aspects of visual information that our brains are actually really good at taking, understanding. So for example, the way of understanding grouping is another aspect of that our brains are really good about trying to figure out. So, you know, we can see, for example, that that second example of the similarity example, like that, our brains immediately see that the square boxes are different from the circles. You know, our brains immediately see that, you know, there's, the first example has, you know, 3 columns of circles, and it's not just 9 circles. Our brains sort of see it's really 3 columns of circles because there's separation there. There's white space. Our brains, you know, recognize that really quickly and say, aha, that's meaningful information, and let's interpret it meaningfully. And again, like I said, you know, if we were to look at a chart of something, it is much easier with the visualization to see where are the cases where the dark blue bars are higher than the light blue bars. You know, there are 3 examples of them in the latter half of the graph, but we see that much faster in the graph than we could ever see in just looking at the numbers and trying to scan down them, trying to understand them. So when we talk about software visualization, there's actually 3 ways that we typically try to visualize software, and that's we try to visualize the structure of code, we try to visualize the behavior of code, and we try to visualize the evolution of code. I'm going to try to take those in reverse order. So like a very simple way that we sometimes visualize the evolution of code is through things like, you know, Git flowcharts. So when we merge to Git, there are some tools that will be able to show us things in an interesting flowchart. We can see where all the merge points are and where branches have been closed off and merged into master or stuff like that. That's a very simple and fairly common way of us looking at the history of our code. If you use something like Sonar, Sonar often has a bunch of tools in there that can show you the change to code over time. So, you know, here's an example where somebody is showing the code coverage of code over time. I haven't used Sonar in about a year or so, and so I haven't seen if it still has that really cool graph. They had this bubble chart that will actually start moving through different versions of the code, and you could set it up so I want to see how the size of the packages move, and I want to see how the, you know, code coverage changes over time. One of my favorite parts of the Sonar system. So those are good examples of visualizations of change to your code base over time. And that's an interesting and straightforward case. There's also a bunch of stuff that talks about visualizing the behavior of code. And so, you know, some people use the visualization of behavior to help you understand particular problems. So here's a graph, for example, that's showing a visualization of a particular type of sort algorithm. You know, it's hard to produce that, you know, like automatically generate that from code, but, you know, it's still a good visualization of how code is supposed to behave. And it's easy to understand the distinctions between different sort algorithms if you look at visualizations like this. It's also true that you can see things like visualization of code coverage and things like that in tools like Sonar. So, the fact that you can actually see that there is, you can deduce information about the state of your code by executing it in certain well understood circumstances, like running all of the unit tests and being able to get information out of that. So you have a sense of how effectively a code is implemented just by saying, okay, we've got 87% code coverage. And I know that we have 87% code coverage because I ran a tool and it analyzed the behavior as it was running all of the unit tests, and it said, aha, I think that, this is what your code coverage looks like. Like, that's a very simple, straightforward example of behavioral visualization. And then it's like the first case that I have to confess, I don't feel I've ever really seen some great progress on in terms of the visualization of code, but visualization of structure of code has been an area that I've often been really interested in. So I've got 1:45 here. If we're going to 1:15, I think that I get to go to 1 o'clock, but people can shout at me at some point if that's not true. So here's an example that I was really interested in a few years ago. So a few years ago, Intelliware tried to build a tool that was doing a bunch of things to monitor the status of code. It sadly didn't go anywhere because SonarCube existed and it was doing a better job of it than we were doing. But I was interested in one particular area of that particular tool, which had to do with code visualization and layerization diagrams. And so there was like this paper that this guy named Edwin Houstus had written about how you visualize information inside of your code. And so I set up some tools where I could actually do package analysis of my Java code, and I could actually find all the packages that referred to other packages, and you create these layers out of them. And so something that has no dependencies, I'm getting a message here, so I think I'm just gonna quickly chat it. Something that has no dependencies, no, I think I'm okay. I have to get rid of this chat box. Yeah, whatever. Something that has no dependencies is considered to be layer 0 because it doesn't depend on anything else. And if something only depends on stuff from layer 0, then that's part of layer 1. And stuff that depends on things from layer 1 or possibly layer 0 is layer 2, etc. And you can actually do some analysis of things and discover whether or not you have a layerization problem inside of your Java package. But this gets complicated because people introduce what are called cycles. And so you have like package A that depends on package B, but it's also true that package B depends on package A. But you can actually graphically represent this information. And so a couple of things I learned is that A, this becomes quickly unwieldy. In any application of any meaningful size, this just starts pumping out so much information that you can't make sense of it. SonarCube has something very similar to what I'm describing. If you look at their dependency matrix there, it's doing something very similar to what I'm talking about. But things I learned in trying to play around with layerization, most of my peers just didn't care. Like they didn't care about dependencies. They didn't have any sense that something had changed when they introduced new dependencies, or even worse, new cycles into the application. Most people didn't even have a very good conceptual understanding of what a package meant. They treated it as just like a folder. So they would say things like, I'm going to make a package for the exceptions because I just want to put them all in one place, and that's what I would use a folder for. And so that's what they would use an exception for. And because of that, I eventually introduced some unit tests into my system that failed whenever cycles were introduced. And it successfully failed when cycles were introduced. And I discovered that people hated that unit test, and they would stare at it blankly and not know how to proceed from that point. So what that sort of tells me is that people don't have the same sort of visual relationship to the code that I had, that I kept looking at the packages and the layerization of the code as meaningful, and nobody else looked at it as meaningful. And maybe that's a failure of communication on my part. I should have been better about trying to say, this actually matters for really good reasons. But I was so shocked by the fact that people didn't have that sort of same visualization that I had, that I was thrown off by that. And so one of the reasons why I think it actually matters is I think that that's the beginning of how you try to look at the code as an artifact, and a code as a thing that communicates its overall design and intention. So what I mean by that is if I have some sort of architecture diagram that is showing, who knows, maybe some tiered architecture, very basic tiered architecture, that looks something like this, where a web tier is talking to a service tier, which is talking to a data access tier, shouldn't I be able to look at the package dependency diagram and see something that generally resembles that? And it doesn't matter if we're talking about a layer first architecture or a domain first architecture, or, you know, ports and adapters or what have you. The code should look like the architecture, I think. And there are people who have written about this particular concept, which has to do with this thing they call the model code gap. And the model code gap, Fairbanks talks about it in his book, Just Enough Software Architecture. He says, you know, the problem is that your architecture models don't look the same as your source code model. And that introduces this cognitive dissonance between what is your architecture of your application and what is your implementation of the application, and why don't they look at all the same? Okay, so just to summarize this point here, I continue to believe that, you know, software visualization is a great tool and can help me, but I also recognize that we haven't really perfected the right tools of software visualization to help me overcome problems like the overwhelming amount of detail. I'm going to make this last assertion, which I'm not providing any evidence for, but which I believe to be true nonetheless, which is that I think that our sense of complexity and legacy are sometimes tied to an absent ability to visualize the code. If we have code where we look at it and we can like easily understand what the overall structure of the code is, I think that we view that as not complex, and we view that as, you know, modern and cool, etc., in a way that we don't view something that that has a high model code gap quality to it. So then that whole visualization conversation leads me into this idea about, oh, well, you know, there was a thing that we used to do in the days gone by, which was we used to draw architecture diagrams. And for some reason, we don't draw architecture diagrams quite as much. And there's a whole bunch of reasons why that is. There's a guy out there named Simon Brown who's done a large number of talks about this particular topic. He blames Agile in many ways. So he says, you know, like Agile seems to have killed architecture and diagramming. And part of that is like, you know, a big part of Agile is this whole idea about big upfront design. And we also need, like, it says basically don't do big upfront design. And it's also true that we have to look at the history of how architecture diagrams really came into our industry. And that had to do with, you know, people who are really good programmers got promoted to this level of architecture and they weren't allowed to program anymore. And so they threw diagrams instead, and they threw it over a wall to some developers who they never talked to and said, now implement that. You know, I'm the smart person. I figured out what it should look like diagrammatically. And now you just could write the code and do that. And that was an obviously awful time in our industry. And nobody wants to go back to that, except that now we've gotten to this place where the visualization of what the code is just isn't as big of an element of our development as it once was. And so, for example, we don't tend to do these things anymore, which are these, you know, UML diagrams, and I don't think anybody likes them anymore. When these things get large, they're completely unmanageable. And if I go back to this point I was making earlier about the values of software visualization, UML is a terrible way of visualizing things because, you know, it doesn't use color, it barely uses position. A lot of the information it provides is really awful. When the people who made UML originally created it, they were really interested in this idea of this one pen design consideration, which is that if you are in a room with a piece of paper and only one pen, you should be able to draw a UML diagram. And so, you know, things like color meant nothing to them and isn't really part of any UML specification. It's also true that a lot of people, when they think about UML, they immediately go to things like class diagrams and occasionally sequence diagrams. Whereas some of the more important types of diagrams, such as, for example, the deployment diagram that I have over here, is one that almost nobody uses and people just ignore it completely. But in many cases, this is one of the most important types of diagrams that you could have in a system because it tells you what are the things you're deploying out to actual physical machines somewhere or even, you know, virtual machines somewhere. And, you know, what goes where and how they communicate with each other. Like, this is the sort of diagram that you want to give to operations people or people who understand, you know, the setting up of boxes, etc. But almost nobody thinks about these types of diagrams, and almost nobody makes them anymore, which is an interesting thing. And so I'm not really mourning the loss of UML, but the fact that, you know, the fact that people have lost so so many of the things that we could get out of UML and haven't really replaced it with something meaningful makes me a little bit sad. And the fact that UML died is understandable given that it didn't really have a lot of great tool support for it. Tool support tended to run the gamut from incomplete and lacking in features to expensive and nobody wants to buy it. And some very special tools managed to be both at the exact same time. And most of the tools that we ran into didn't really have support for multiple programming languages, or they were completely agnostic about programming languages and didn't have any ability to do any sort of round tripping, etc., which is even worse. And then finally, a lot of people just think it's not cool anymore because we live in a world of agile and nobody wants to do UML diagrams. And I get it, I don't want to draw UML diagrams anymore, especially if if it's going to be a lot of work and the tools are really bad. But there are some positive elements about diagramming that I think are interesting. I think I have about 4 minutes left, so I'm going to kind of race through some of my last slides here. There are some tools out there these days like Plant UML, which are starting to provide some alternative ways of dealing with diagramming like UML. So they allow you to do things like write out in some specialized notation what a particular diagram should look like, and then run a tool against that and generate a diagram programmatically off of it. It's not the best diagram because it's kind of making its own decisions about how to lay it out and what does left and right mean in any of this stuff, etc. So this one, with my very simple notation, decided to draw this diagram with the thing about the other thing. It's is that a useful way of visualizing or positioning these things? Who knows, etc. But the appeal of this is that I can take that little text file that generated that diagram for me, and I can commit it to my source code repo, and I could run that Plant UML as part of my build, and that's a really cool thing. And then that diagram lives alongside of my application for all time. And if our developers are conscientious, which is a huge if, we can update it over time as our code base changes. There's also a recent interest in these really nasty diagrams, which I just think are horrible. As cloud becomes a more bigger part of our development and world, we're increasingly seeing nasty diagrams like this, where everything is represented by specialized icons that nobody really understands. There's no real good entry point to these types of diagrams. This is an AWS system that somebody has created somewhere. I think it was built back during the great arrow shortage of 2018, because for whatever reason, there's all these little boxes, but there are no arrows that are connecting them. And these are really meaningful if you've gone through the whole process of trying to understand what all of these icons mean in advance, and you're deeply familiar with being able to translate this into AWS concepts. But until you have all of that background knowledge, this is an impenetrable diagram, which I think is really sad. And then we have to contrast that with the whole agile orthodoxy, which is to just, write things on a whiteboard and have a conversation about them instead. And I think that there's value in that, but I don't think that is the entire solution to visualizing and diagramming of applications. So having a whiteboard conversation around something is valuable, but it's transient. So it is valuable for a short period of time, and then the people who are involved in that conversation move away. Or just forget the conversation over time. The diagram itself is rarely comprehensible beyond the memory of that particular conversation. So you might have some boxes and you've drawn only enough information to satisfy what it is that you're talking about at that particular time. And you still have all those problems. At some point you have to hand this over to an external party or somebody else who's going to take over your job or something like that. And they weren't part of that original conversation. So the diagram that you created is only half of the experience of visualizing that particular architecture. This is a point that Simon Brown goes on to at great length, and he's tried to address using his C4 model, which contains a lot of really interesting guidance. So he's created this architectural recommendation about how you should diagram your application in a way that that is comprehensible and that people can understand it, et cetera. And a lot of his recommendations are really quite good. He also deals with, his C4 model uses the idea of abstraction a great extent. The fundamental abstraction, the problem that abstraction fundamentally helps us deal with is that our brains can't usually handle a whole lot of detail. So we can reliably handle 7 ± 2 things. And the only way that we can increase the amount of detail is by increasing the level of abstraction. And so Brown's model I'm just going to skip over this because of time. Brown's model says, let's talk about diagrams at 4 different levels. You know, the lowest level is your code class level, and that's essentially equivalent to a UML class diagram. But then he has 3 other levels, which he calls component, container, and system context. And sadly, these names are in great collision with other industry terms. So container, for example, everyone thinks about Docker containers these days when they hear the term container. And so therefore it's a terrible name. But he's basically if I were to map these to additional UML diagram types, these are essentially equivalent to a component diagram, and the top 2 are 2 different views around a deployment diagram. And I like the guidance that he's giving us, and I like the idea that he has this idea. I have a couple of issues with it. So one, I think that there's no level that talks about sort of network layouts, which are increasingly important when we talk about cloud-based environments. And then also, I find that the diagrams that he produces are ugly. They are imposing levels of blue, although they contain better level of detail than exist in most diagrams. I can't stand the output of this. But I do like the idea that the tooling that he ultimately created for this was driven by, you know, things that he could check into GitHub. So he could say, let's have the ability to write a simple class that describes what the overall architecture is. And when I run that simple class, it produces these diagrams directly out of that code. Unfortunately, the problem is that the tooling that he's used to create those diagrams, he's started to brand now, and he's become a software vendor. So the tools themselves are no longer as available. And he's now basically a vendor in this space called Software Architecture Design as a Service, which has the unfortunate acronym of SADAS. But if you're ever so inclined, I'm 2 minutes over my time, but I'm very close to the end, so I'm going to race through my last couple of slides. If you're ever so inclined, there are a handful of guidances that he offers about information that you can add to your diagrams to ensure that they end up being better. And I like the guidance. I just wish the overall tooling was better. So basically, his 2 key arguments are that architecture diagrams are good and necessary, and there's a certain minimum amount of information that needs to appear on them. And if your project has no architecture diagrams, you're a bad person and you should feel bad. But the other argument is that code should reflect the architecture, which I really agree with. And he approvingly quotes Fairbanks, who says, you know, what you really want to have is something called architecturally evident coding style. And what is that architecturally evident coding style? And it could mean a lot of things, but there are a bunch of ways in which we could actually divine the architecture from code. And it's helpful if we actually have a visualization of it early on. So we could, for example, figure out what are components by annotations, by naming conventions. If you're in a language that supports namespaces or packages, you could look at packages. You know, if you're in a language that supports different types of modules, I think I've seen exactly 1 project in my life that used OSGI modules, but Maven modules is a very common thing for Java world. If you're in Java 9, Java modules is another thing, etc. Even microservices is a way of breaking down things into modules. So my conclusion, I think that if you code in an architecturally evident coding style, you're more likely to be able to visualize the architecture, and that actually helps you, A, with the overall implementation of it, B, with the overall life cycle of that particular coding style, and C, in terms of anytime you have to hand this off to somebody who is new, if they can perceive what the architecture is, then that's even better. And if you do that well with a bit of information, additional information, and perhaps a bit of additional tooling, you might be able to generate diagrams off of your code. And I think there's some really neat exemplars out there, such as what is being done with Plant UML and the C4 stuff. And lastly, I think diagramming is good. I think transient whiteboard diagrams can definitely provide short-term value, but are insufficient as a long-term project artifacts. And that's it. According to this, I'm 4 minutes and 49 seconds over the 1 o'clock moment. And I think we're at that wonderful time where we're trying to propose questions.
First of all, thank you, Steve. That was an amazing talk. Got a few cameras, yeah. If anyone has questions right now, we have about 10 minutes for a Q&A session. If you want to post any of your questions in the chat, feel free to do that. we'll give about like 1 or 2 minutes to see if any questions pop up. Oh, we've got one right here.
Ah. Did I create that cycle detecting unit test with Arch Unit? I did not, actually. I used JDepend and some cyclic code analysis stuff that I had written. So I had a base unit test that I would apply to each project I would join, and then I would specialize it just to be able to find all the packages for my particular project. In fact, I don't even know about Arch Unit. Maybe I should look into that. Thank you for the suggestion. Question, what about the open source programming language processing, which is a visual programming learning platform for non-programmers? Do you think it has untapped and generalizable potential for industry use? I would love to be able to answer this question, but I've never used it. It sounds really interesting, though. I would love to try it out and figure out what the answer to your question is. Thank you for recommending it. Wow, already 2 questions and 2 new tools I've never heard of. Does Plant UML overcome the challenge that you mentioned of reducing visual representation to the common denominator of the code? No, I mean, Plant UML is basically, at the moment, Plant UML creates diagrams using the text files that are completely divorced from your code. So you basically can make your Plant UML diagrams as complex as you want them to be. What would be ideal is some sort of gap closing tool that would help you to detect and find the interesting bits inside of your code and figure out how to generate that interesting little text file out of that, and then use that to generate the diagrams out of it. At the moment, I'm unaware of any open source or widely available component that actually allows you to bridge that sort of Plant UML to code world. But I think that, you know, I would love to see it, and on various times when I feel like I have too much time, I try to imagine if I could actually start trying to write one of those. Next question, since full face design method is not encouraged, does this mean that the architecture should reflect a minimum is best? Not 100% sure I understand the question, but I think that the question is, are we trying to, am I eschewing the idea of trying to diagram every last aspect of the project? I think I would. I think I would eschew that because I think that, you know, there's so many parts of the application that are just easier to get right when you actually have running code in front of you. So what's the rest of the question then? Should it reflect a minimum at best? I think that I wouldn't articulate it as it should reflect a minimum, because I think that it's too easy to make diagrams that are overly simplistic about the architecture. And sometimes overly simplistic is the level of detail that you need to talk about. But I think you need to be able to get to a couple of other levels of detail. So that's one of the reasons why I think that Simon Brown's C4 model is interesting, although I have reservations about it. I think that he recognizes that there's a value for a very high level picture that you can drill into to at least a couple of additional levels of detail. And if you can drill into those additional levels of detail without getting overwhelming in terms of the amount of detail that you're seeing, then I think that that's your architectural ideal. I think that being able to visualize necessary detail when necessary, but being able to abstract and go up to a high level when that's the level you need to talk about. How can I write better architecture diagrams? I'm a boot camp grad and constantly work with folks who create a lot of diagrams. I'm trying to get better at documenting architecture. Are there any ground rules apart from what you've already mentioned? Are there any good examples out there that I can follow and use as a reference? So the first thing I would probably recommend is go out and find all of Simon Brown's YouTube videos, because I think that he covers a lot of these concepts really well. In particular, tragically, I think that he's done like 3 presentations, maybe only 2 or 3 presentations, and he's repeated them with slight variations in multiple different conferences around the world. So if you go look for his presentations, you'll often see him talking about the same concepts in a wide variety of different conferences. But find his presentation on visualizing the architecture, find his presentation on modular monoliths, and watch those a few times. That would be a very good start. I think that he covers some of the really good topics about visualizing software in that, and not visualizing software, but creating effective architecture diagrams. That would be my first recommendation. And then if that really speaks to you or appeals to you, then it can't hurt to review the Martin Fowler's UML book, although I think a lot of people are moving away from UML for reasonable reasons. We have a question here. I started off talking about representations in different dimensions. Do you think it will be easier to understand architecture diagrams that are not always in 2 dimensions? That's a really interesting question. In particular, it's interesting because I've recently really gotten into 3D modeling with a tool called Blender, and I'm really enjoying it, and keep trying to imagine how I could push 3D modeling in various different ways. So I don't really have a clear and certain answer to your question, but there's a part of me that believes, without evidence, that there is value in trying to deal with architectural diagrams that are not always in 2 dimensions. In particular, I think that there are certain types of dimensions to diagrams that don't lend themselves well to representation on 2 dimensions. So for example, when we start dealing with questions, sometimes you want to have an architecture diagram that defines sort of the structure and layerization and maybe the deployment picture of things. But there are other dimensions you want to have in diagrams, like, when you're dealing with scalability and fallover, like that almost feels like it's a completely separate dimension on a diagram. And if you could actually deal with something that a diagramming tool that can show off multiple dimensions, I think that's really interesting. Although there's a part of me that worries that, those will quickly become overwhelming, or you'll run into situations where you want to be able to see what's in the back corner, and it's hard to, because unless you can rotate the entire diagram, etc. So I have random thoughts on that question, but no answer, I'm afraid to say. And Rory has posted a video about 3D architectural models.
I think Deepika, I hope I pronounced your name right, had a question right above Jen's.
Oh, you're right. Yeah. I apologize. When should an organization think about using a visual programming tool for their code base? Yeah, so visual programming tool is an interesting thing. So I'm talking about diagramming and visualizing architecture from the code base. There's been a really weird history in our industry about trying to come up with tools that allow you to draw pictures and auto-generate code off of that. And for the first 25 years I've seen this, it's been terrible. Like none of those tools have worked well because they fundamentally don't seem to deal with the parts of code bases that are necessarily complex. Like I've seldom seen a visual programming tool that has been able to deal with, say, an if then else tree of any level of complexity. And so almost every example I've seen of somebody trying to actually write code using a visual tool has been bad, unless they have the ability to just break out into and type in their own this is my method implementation at this particular point at this. And I certainly don't think that I've seen examples where anything has developed a certain degree of industry buy-in. So there isn't an industry leader in the visual programming space. But I kind of feel like we must be getting close to the point where we can crack this particular problem. In particular, I'm again going to use the example of Blender because it's something I've been spending a lot of my free time with. One of the things that people do with Blender is they have to apply materials to things. So if I want to have an image of something, but it's a thing that's rusty and metal and has dirt around the edges of it, there's this whole process where you have to be able to apply the metalness of the material, the rust that appears on the material, the dirt that sits on top of the rusty metal of the material, etc. And often the mechanism for doing all of this is complex math, except that Blender as a tool and several other 3D modeling tools as tools have this wonderful node system where people can connect things together, and people who aren't programmers, who are visual artists, are able to use these node modules or these node representations of the metalness to create really sophisticated and complex effects, almost and do a whole bunch of things that are almost the level of programming, even though they're not really programmers. And I just think that that's really inspiring, and I feel like, you know, we must be close to the point where we can take inspiration from examples like that and say, this kind of thinking about the way that we create something must be applicable to the programming world. And I just have sadly never seen anybody really succeed in that. Okay, have I gone through all the questions?
You sure did.
Oh.
Thank you. I think we're at time too. So just want to say thank you again for an amazing presentation. Even based on the responses we see in the chat, everyone loved it. So thank you for your time. Thank you to Intelliware for being a staunch supporter of WWCode and of the Toronto chapter too. You all are amazing. And thanks again, BC.
Thank you.
Thanks everyone for coming out. We're calling it a day. See ya.